recording. It doesn't hurt. And I think I was saying, but I don't know if you heard me, there is a procedure to record yourself present to the class. Since you're here and listening to me, do it. There is no cost if you have your agenda in sight, which should be the case. All right, so yesterday I left you this point, and the point I was trying to make was that there is a danger with vector autoregressions, and the danger is that they are very richly parameterized. And you can see the reason at the bottom of the slide. I already did that with you yesterday, but if you count the number of coefficients that in principle you have to estimate in a vector autoregression of order p, you will find that the total number that you get is quite scary. And the reason is that in a couple of places of these, quantity that you have at the bottom of the slide, let me emphasize that, you have n square. You have a one n square, which comes from the, covariances, which are inside the covariance matrix. That's already scary. But especially you have these n square times p, and this implies that if you specify very large VAR models in terms of number of legs that you put on the right-hand side, you will have many parameters to estimate. And talking about ARMA models, we already saw what the dangers are when you over-parameterize your econometric models, which is you can get a very good fit to the data, but at the risk of degrading, of lowering the quality of the forecasting power. And the story is that if you have many parameters, the algorithm of estimation starts using some of those parameters not really to fit the structure, the process, the DGP, the population dynamics from which the data come from, but some of the parameters, they are used to actually fit the little jump, the little spike, the little through that you see in the data, the little odd observation. Now, those jumps, spikes, odd observations, they are like black swans. They will not occur very frequently. And yet, the parameters that you are estimating, they will stay with you throughout your entire application, and they may cause damage by indeed lowering the accuracy of the prediction that you can perform. So in the case of VAR models, more than ever, a sensible selection of P, the number of legs, becomes crucial. I also mentioned yesterday the case in which you try to estimate a VAR, in which you have more parameters than the number of observations, which philosophically speaking should not be possible. But when you can apply to VAR's OLS estimation equation by equation, then you may be tricked into doing that, although it makes no sense. Okay, so how do you select P? As always, there are a variety of methods. We speak about the most common ones. There are other methods, and there are methods which are not codified, meaning there are sensible ways to guard against the over-parameterization of the VAR models that cannot be really stated in formal mathematical or statistical terms, but they may be equally valid. Number one, and I would discourage you from using it, even though I mention it. Some people, especially when you can perform OLS estimation equation by equation, they love to take the single regressions which are part of the VAR and apply t-tests or f-tests. You know that t-tests are to test whether the individual coefficients are statistically different from zero. So if the corresponding variable, the corresponding leg should be included. The f-test, they are equivalent to the t-test, but they are applied to multiple coefficients at the same time. So you can use them to test whether chunks of each regression, they can be dropped or not. Now, in the case of VARs, even though you are estimating them equation by equation, this is not a good idea, because a VAR is a system model. It is a system of regressions, a system of linear stochastic equations that we want to estimate. So even though we have the, say, ease of sometimes being able to use OLS equation by equation, it doesn't mean that a VAR is just a collection of regressions. So it can be done. Sometimes it is done, but it should be discouraged. Why is it done? Because it's very simple, right? So once you do econometrics 1, you need nothing else, even though you are faced with a vector autoregression. Notice that if you kill coefficients in each individual equations using t-tests or f-tests, you're running into a contradiction, because after you remove the coefficients, you remove the legs, this means that the VAR, even though it's a reduced form VAR, now has, you should shut up, sorry, now has restrictions. And you know that even if the VAR is in reduced form, once you have restrictions, that you have constraints imposed on the VAR, you can no longer use OLS. So it's a strange situation in which you do OLS, you kill coefficients, but then you're stuck in a situation in which you can no longer apply OLS, and you have to resort to GLS, maximum likelihood, the things which I mentioned last time. So, all right. Number 2, this is something that was reviewed at the very end of the prep course, but as you know, the slides are posted, so you can pick them up again if you want. It's typical to apply likelihood ratio test. In this case, they are actually applied to the log likelihood, but the principle is the same. What is a likelihood ratio test? It corresponds to a very simple idea. If by dropping parameters, coefficients, the maximized likelihood of your problem, this implies that you're doing maximum likelihood estimation, of course. If by dropping parameters from your model, the likelihood function that you're maximizing does not go down significantly, so it remains similar to the initial likelihood function, then this is evidence in the data that you can actually move in the direction of dropping those parameters that you are testing. So you have two situations. The initial situation in which you have a full set of parameters, and you estimate the model by maximum likelihood, so you maximize the likelihood function. And then you try to remove a portion of the parameters, just one, a few of them. You lower the P, so you lower the number of legs that you have on the right-hand side. And you redo the optimization, you re-optimize the likelihood function, and you get the second restricted likelihood function. Now, logically, if by removing a bunch of parameters, the likelihood function does not drop much, then it means that those parameters could have been dropped without significantly disturbing the fit to the data of the model. Now, obviously, in reality, you're not just computing a number, computing another number, and just looking at them, or like computing the percentage drop. Formal statistical theory allows you to perform a formal test, and such a test is called the likelihood ratio test. Now, in reality, if you look down at the slide, you do not see a ratio. The reason is that, as I explained now 3 weeks ago, more or less, when it comes to do maximum likelihood estimation, often we are actually maximizing the logarithm of the likelihood function. And the reason is that it's the same, so it gives the same optimal estimates, but it's numerically more stable. But remember that if you take the log of a ratio, the log of a ratio is the difference of the log of the numerator and the denominator. And so that's why, even though it's called the likelihood ratio test, at the bottom of the slide, in parentheses, let me show you here, you find a difference, not really a ratio, but it's a difference of logs, and so it is the same as the log of the ratio. So it's practically the same. Now, what are the objects involved? There is a scaling factor, which is a function of the number of observations, capital T, the number of variables, n, and P naught. P naught is the is the final number of parameters after you have imposed the restriction. So you use the lowest number of parameters of coefficients. And then there is this difference, which I have highlighted in the slide, and this difference of log of strange objects. These objects are determinants. So when you put things into bars, you see the bars, I think. Typically, you're thinking about absolute value, or you're thinking about module. But when you put in bars the matrices, a matrix, like in this case, sigma is a matrix, then this is to be read the determinant. And basically, the determinant is like the size, the number that condenses the size of a matrix, how big, how small a matrix is. So that's why we use the same notation. So what you're taking inside the parentheses is the difference in the log of the determinant of the sigma matrix when you impose restrictions minus the log of the sigma matrix when you have no restrictions. Why the sigma matrix? Well, the sigma matrix is the estimated covariance matrix of the residuals. And it turns out, so something which I state without proving, if you look at the book, there is the proof, that in the case of VAR models, to speak about the maximized log likelihood and to speak about the determinant of the covariance matrix of the residuals is equivalent. So they give the same numbers. There is a proof, mathematical proof for that, but it is much easier to do things this way. Now, as always, in statistics, when you apply tests, you have to know the critical values. So you have to know what is the distribution of the test statistic under the null hypothesis. The null hypothesis in this case is that the original number of parameters was sufficient, so it was enough to fit the data. And it turns out that asymptotically, so this is an asymptotic result, really, okay? So as always, we are invoking the possibility of the number of observations we have available to diverge to infinity, but it turns out, you can prove once more, that this quantity that you see, LRT, asymptotically converges to, so it becomes distributed as a chi-square with a number of degrees of freedom equal to n squared times p1 minus p naught, where n squared times p1 minus p naught is the total number of restrictions of coefficients that you kill when you go from a number of coefficients equal to p1 to a number of coefficients equal to p naught. So when you basically lower the dimensionality of your VAR model. Okay. So in the next slide, I basically explain the principle which I already told you about. Now, the important thing to understand, you will see one example in the next slide, is that this test can be correctly applied to specify the number p, so the number of legs that you want in a VAR, going from the biggest model to the smallest model. So the way you perform is that the starting point is the number of parameters that you have, and you try to reduce it, and you test how much the log likelihood function drops after you have restricted the value for p to actually decrease by one or more ticks. So you do not have to decrease p by one at a time, but you can do whatever you want. But the test remains the same. Now, careful. So technically, the stated asymptotic distribution for the LRT test applies only if the residuals, the errors of your model, are normally distributed. Otherwise, there is a double approximation in the sense that the chi-square result is already an asymptotic one, and there is another order of approximation because the shocks were from a distribution different from a normal one. It's not always clear that the chi-square distribution provides a efficient estimate of the true distribution under the null hypothesis. Now, for most practical purposes, even though people understand what I just said, this is ignored, and we just happily use the chi-square distribution, and that's kind of accepted in terms of practical applications. So what is the beauty of this method? It's a formal statistical test from which you get either rejection of the null hypothesis, which means that you can simplify your VAR, or not. So you do not reject the null hypothesis, which means that you have to stick with the bigger VAR, so the bigger size VAR. What is the disadvantage? Well, it's an approximation, because technically this holds only if you have an expanding sample which goes to infinity. And second, there is also the issue of assuming normality of the errors, which may introduce a further layer of approximation. Now, in reality, you will see the example. When people try to use the likelihood ratio test sequentially to study the order of the VAR, what is commonly observed is that the resulting VAR tends to be kind of big, very large. So it's not a very parsimonious criterion in spite of its optimality. What I mean, see the prep course if you are curious about what I'm talking about. The likelihood ratio test among all tests is the one satisfying a famous result, which is called the Neyman-Pearson lemma, and which basically states that if a test of hypothesis is structured on the basis of the likelihood function, as this one is, it will be the most powerful test that you can find. So the best test in terms of rejecting the null hypothesis when you need to. But people sometimes they just apply without even thinking about the optimality property. All right, now, so this test is quite, I mean, it doesn't look like, I know, but software will apply this test as a matter of routine, because for software computing these covariance matrices, taking the determinant, taking the log, and taking the difference is a matter of a fraction of a second. So these numbers will pop out, I mean, in a stream, basically. You do not see your computer even thinking about it. The problem is that because we apply VARs often with small data sets, small samples, especially if you think about macro, they are not really effective. So usually they are not really helping you to select down the order of VAR as much as you would hope for. So there is another set of criteria, of methods, which are commonly applied, and we have encountered them already. These are information criteria. In practice, the information criteria that we have seen in the case of ARMA models, ARIMA models, they can be generalized to the multivariate case. So instead of AIC, you talked about MAIC, instead of SBC, MSBC, and so forth. And they have the same structure as before. So if you go back and you compare with the lecture on ARMA models, you will see that it's totally the same. The only difference is that the first term that you have in all of them, which is actually common, if you notice, this guy is repeated 3 times. It's not just the sum of square residuals, that's the way it was called at the time, with the log in front of it, but it is the log, the natural log, or the determinant of the covariance matrix of the residuals. So the notion of sum of square residuals is generalized to a multivariate context by becoming the determinant of the covariance matrix of residuals. Otherwise, the logic is the same. K in this case is equal to the number of parameters in the intercept vector n plus n squared times p, which is the total number of parameters that you have inside the p A matrices. So A1, A2, dot, 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 AP. All of them, they have n squared elements inside them. And the logic, as always, I explained already why, so go back and review, it applies fully to this case, is that you want to minimize information criteria. So that's the only thing that you need to remember. Do not maximize them because it would be dramatic. Okay, here is one example. The application, I think, is to the to a VAR for 1 month, 1 year, 5 year, and 10-year US Treasury yields, so interest rates, which is an application that is also used later on in this lecture. In the table, you have a column in which you have P, the number of legs. When P is equal to 0, you're really looking at a model with constant mean and constant variance. So you're looking at a model without any predictability. Then you have the maximized log likelihood. And obviously, there is a big jump up when you go from no VAR to the presence of the VAR. And that's not surprising because interest rates are very persistent, and so they seem to require some legs on the right-hand side for you to be able to explain, to predict them. All right. Then you have a column in which you have the likelihood ratio test. So it's called the LR in eViews. This is an output from eViews. LRT would be best. And then I will tell you how to read it. Then you have a column which I actually muted. It's another criterion, not very popular, I must say. It's called the forecast prediction error. So I don't want to speak about it. eViews has it. I don't know why, but okay, it's there. And then you have the column with the AIC, so the archaic information criteria, the Schwartz information criteria, also called SBIC, and finally the Annan-Quinn information criterion. So let me start from the information criteria. You want to minimize them, and here is one more case in which Schwartz and Annan-Quinn, they get along, they agree. They suggest to specify a number of legs equal to 2, and AIC is actually much less parsimonious because it suggests using a VAR with 11 legs, which is a lot of parameters to be estimated. To be precise, in this case, it would be 11 plus 11 square, plus 4 square, which is 16 times 11. So I don't know, 16 times 11 is 176 plus 11, 187 parameters, which is a lot of parameters to be estimated. In this case, we have enough observations. That's not the problem. But imagine presenting to your colleagues, to your desk, to your boss, a table in which you have 100 and, what did they say, 87, something like that, 187 estimated coefficients, 187 p-values, right? So, I don't know. But the Schwartz criterion and the Anand-Quinn, they are much more parsimonious, and they point to quite a typical VAR2 model. Now, likelihood ratio test. So here is a puzzling object, because typically I, and you as well, that's natural, you tend to read it from top to bottom, right? And there is nothing really here to interpret. You have to go to the critical values of the chi-square distribution. But okay, these are big values, but I mean, then some of them, they get kind of smaller, like 25 here. There is a 24 here. And then suddenly EViews with this star is telling you that this criterion wants to select 14 legs, which is a lot, which is crazy, but okay. Now, many people at this point, they, office hour, for instance, they come up to me and they say, okay, I see the 26 with the star, but I don't understand, because I thought that 26 is actually bigger than 25. So why isn't EViews stopping at 9 and it goes up to 14? The mistake is that you're reading this column from top to bottom. And as I told you, in the case of likelihood ratio test, we should apply them starting from the biggest model and going towards the simplest model. So it needs to be read from bottom to top. And this star appears here because just above it, these 3.39, see here, in correspondence to 13 legs, is the first value for P, such that the null hypothesis that the bigger model can be simplified down to a smaller model is rejected. And so you need to stick with the model with 14 legs. That's the way you read it. So you read it from the bottom to the top. And this is quite common. So when you have tables like this, usually you have information criteria giving you pointers towards the optimal P up here. This case, I mean, AIC is really going for the nutty stuff already. And then the likelihood ratio test is giving you indications of number of legs down here in the table. And usually, so LRT is not very much followed. But to compute it, especially because EViews does it for us, cannot hurt. Okay, let me tell you a few words about forecasting, but I've got nothing new to say. Meaning, if you take an AR model, and we already had that class on forecasting with ARMA models, if you specialize to the case of AR model, and instead of forecasting one time series, you are forecasting a vector of time series, y, t plus h, bold-faced, like in this case. If you apply the things, the principles which we said at the time here, you are all right. So what did we say at the time? We said, I think, two things refer to autoregressive models. First, that in general, it's not clear how you should produce a forecast from the model. But because this forecast, so the way you go from the model to the forecast, should depend from your loss function, which is the pain you feel every time you make a prediction error, a mistake. But if your loss function happens to be special, it's a square loss function, which is the same loss function that you use when you are estimating by OLS, then the way in which you squeeze out forecasts from your estimate of the model becomes simple, because the conditional expectation is the optimal forecast from your vector autoregressive model, which is what you find at the bottom of this slide. It's just a reminder of something that we saw already together. The other thing which I told you about autoregressive models is that the forecasts are computed in a recursive fashion. So as long as the past values of y on the right-hand side of the VAR, they belong to your information set. So these are past values that you've seen already. You use them, of course. But when the forecast get longer horizon forecast, so that basically you have forecast of the future, which in principle depend from other shorter term forecasts of the future. So you have forecasts on the left and on the right of the equal sign. Then the forecast on the right are replaced by the forecast that you must have recursively computed already using the model. So it becomes just a recursive formula in which you plug in forecasts to produce other forecasts. Two comments. First, this business of having forecasts depending from previous forecasts is such that in the very long run, so if the forecast horizon H goes to infinity and your VAR is a stationary model, you know what must happen. So you can also prove it that algebraically, but you know the stationary models, they're called stationary because they tend to revert back to their point of attraction. And the point of attraction, being a stochastic model, is represented by the unconditional mean. So if you have forecasts for the very long horizon, such forecasts, they must be progressively get closer and closer to the long run mean. So that if I come to you and I ask, look, what is your forecast from this VAR, say 2,000 years from now, without doing calculations, probably you should be happy to say, well, the unconditional mean. I mean, it may not be exactly the unconditional mean, but for all practical purposes, it will become the unconditional mean. But these relies on stationarity. Forecasts can be computed also for non-stationary models, but I don't know the sense of the exercise in that case. So that's the first one. I wanted to say something else. Two comments I said. One is this. It's gone. All right, maybe it will come to mind later, but this was the important point. Okay, so careful with the long run horizon forecast because we know how they must behave. Okay, then we'll play with eViews. eViews has routines to produce automatically forecasts, which are very nice, and it allows you to plot the forecast, to visualize them, to analyze them, and just a few clicks. But what is going on behind the scenes is exactly this recursive formula applied many times. Okay, now the next thing I want to talk about is so-called multivariate analysis. So why do we estimate VARs? The immediate answer is, well, to look at the coefficients and to say things. Okay, maybe. But remember that in a VAR model, there are so many coefficients that sometimes to tell a coherent story for what is going on will not be very easy. All right, so even just the act of presenting tables in which you have 20, 40, 60, 176, whatever it was before, coefficient is a bit the challenge. So one. Second, the real answer is that because you want to forecast. And the machines have gotten very good at doing that, and then you have to judge the quality of the forecast. So you will see examples in the lab with me as well as recorded very soon. But there is an entire family of analyses which follow the estimation of a VAR, which are not equivalent to forecasting. They're related to forecasting, but they're not the same, which have become very famous. And in fact, there is a big business of people who estimate VAR without a straight intent of forecasting. But what they want to do is one of the three following things. First, compute, plot, represent, discuss impulse response functions, number one. Two, let me go there. Some people, instead of impulse response functions, they want to plot or tabulate variance decompositions. Now, I will show you that variance decompositions and impulse response functions, they kind of contain the same information. So they are like two different ways to represent the same numbers. The numbers are not identical, okay, but it's very easy to go from one to the other and back. So if I give you a variance decomposition, then you should be able to compute an impulse response function. I'm not saying that it will happen, okay, but you should in principle, and vice versa. And finally, some of you maybe in this class was actually mentioning that, I think in the last class. Some people, they estimate VARs because they want to test for causality. We will have to be careful because the causality that we will be testing is not the causality that philosophers are writing about. It's kind of a statistical causality called Granger-Simms causality, and it has to do with forecasting power. So again, we are 1 inch away from forecasting, but we are not really only caring for the forecast and their accuracy, but also for other things, which I'm about to explain. So let's go back, which is always is a job in itself. All right. So VR models are used in practice with the goal of understanding what dynamic relationships exist between or among the variables of interest, which are the variables which appear inside the VAR. And the main tool with which you do that is through the calculation, representations, plotting, say, of impulse response functions. What is it? Let me show you just one case, because I think that it's better to have a visual instead of words. These are already impulse response functions, but these ones are nicer. So the impulse response function traces how a variable that you have in your vector, in your VAR, will react between the current time and many periods ahead, as many as you want, to a shock of standardized nature, to either the variable itself or to other variables, a shock that is given at time zero. So I repeat, how over time a variable in your VAR will be reacting period by period up to some point, which you can determine, as a result of either the very variable that we are discussing or some other variable in the VAR being shocked by a standardized amount. Usually people apply one standard deviation shocks, but you do not have to. And you will see the software allows you to specify how big is the shock that you want to experiment with. So what are you really doing is to take your VAR, set all the epsilons, the u's, the residuals, whatever they are, the errors, equal to 0 but 1. You want to shock that by a standardized amount that you will write in your report, in your work, and see over time how that variable, as well as all the other variables, will be reacting to such a shock. Okay, and the type of pictures, the type of, say, analysis that you produce is something as the one that you see in this slide. So there is a blue line which represents the reaction of the variable between time 0 and time 52 in this case. These are weekly data, so 52 is 1 year. So you are tracking the reaction of the variable for 1 year. There is usually a natural comparison with a 0. So initially this variable, whatever it is reacting by jumping up, but then the reaction is actually lower and lower. It gets weaker over time. And at one point, the reaction, in fact, changes sign. So it becomes not a positive, but a negative reaction. Now, there is one thing. So these VARs are stopped at 50 periods after the shock, all right? So you can actually make the plots longer or shorter. So you will be in control of that. But there is one thing we know. If your VAR is stationary, over time, the shock will be forgotten, because stationary models are models which may have some memory, but eventually they must forget all the shocks and therefore go back to the unconditional mean, which is a property which I just invoked a few minutes ago. So we know that these functions can go up and down. Some of them, they can be pretty funky, say, have like funny behaviors like this one that you see here. But eventually, in the long run, if the VAR is stationary, they have to go back and touch, or at least get very close asymptotically to the 0 axis, because the shock must be entirely absorbed, we say, or forgotten by the model. Now, in this case, the blue lines, they do not seem to go very happily back to 0. And this means that when you're dealing with this type of variables, these are US interest rates. So the variables are very persistent. As you will see, between today and the following 2 weeks, in the case of US interest rates, there is some doubt as to whether they are stationary or not. If they were non-stationary, so if they were random walks, then there would be no reason for these blue lines to go back to towards the 0 axis. But it seems to work okay. Here there is some evidence that this guy is going back towards the 0 axis. Maybe you can imagine some evidence also here, but apparently 50 periods are not enough. Okay, let me go back. If you read the definition, I will not, but it contains the same info, I hope, all right? And so you're tracking exogenous shocks to one or more variables. Typically, it's applied to only one variable, right? It's a clean experiment in which you shock one of them and you see what happens to the others. But, you know, I mean, I've written papers in which the idea was to shock 2 variables at a time. In the lab, you will see such idea push forward actually applied in practice. And the point is to see how the endogenous variables react to the shocks. Notice that what you're shocking is the epsilon, the u's, so the errors, let's say epsilon from now on, and what you are measuring is the reaction of the y's, not the reaction of the epsilons. So please be careful with that. Now, The way you do this, so the slide tries to tell you, but it's best summarized in words, is that if your VAR is stationary, there is a walled representation for the VAR. So you know that all stationary time series, including VARs, can be represented as infinite vector moving averages, in which the coefficients of the moving average representation, called the theta i's, these are matrices in our case, they are function of the original matrices of your model, of your VAR. Like in the VAR1 case, which is the easiest case to think about, the theta I matrices, we saw that yesterday, they are equal to the I power of the A1 matrix. And I just speak of the A1 matrix because in a VAR1 model, there is only the A1 matrix. Okay. So even though it's a VAR, you can rewrite it as YT equal to the mean, the unconditional mean mu, and now we know the formulas for the unconditional mean, plus an infinite sum of vectors of legged shocks, the legged U's, say, that you see here, multiplied by thetas, where these thetas are a function of the original parameters that you had. In this case, they're just A1 to the power I. Now, if you look closely, this relationship is the relationship between Y now and the shocks which happened in the past, in which the relationship is mediated, so it features coefficients. It's a linear relationship. So if I shock at one point in the past the one element, even just one element of U, these will propagate to the future through these theta I coefficients, and I can do the calculations. Now, the beauty is that computers are very good at transforming VARs into moving average representations, applying the Waltz theorem. They just do that in the back end of the computer. And if you ask to compute represent an impulse response function, they will just go pick out coefficients from these theta I things and plot them for you. So practically, the picture that I was showing you, these type of pictures, are just picking out values from the theta I matrices and representing them for your use, for your vision, say. Now, to be precise, what normally we care for is not really shocking the U's, but shocking the epsilons. What is the difference between U and epsilon? U are just residuals. They are reduced form residuals. In all VARs, as you know, they can be represented in reduced form. Sometimes they're born in reduced form. That's what they are. And sometimes, however, they are just represented as such. When they're just representations, however, what you want to shock is not the U's, you want to shock the epsilon. So you want to give shocks to the structural errors. Why so? Because only the structural errors, they are uncorrelated with each other. And so if you shock one of them, you're giving a pure shock. So if you give a shock to the U's are correlated contemporaneously. And so if you shock one, also the others have to move. And by how much, it will be determined by the covariance matrix of the U's. But the epsilons, they have no covariances, so it's just a diagonal matrix, they're covariance matrix, and so this provides a definition for a pure shock. Now, if you're doing a simulation experiment, do you prefer to give clean shocks to just one variable at a time, or to shock everything? Well, just one variable at a time. This shocking one variable at a time is the notion of partial derivative, if you think about it. So how much does Y change if I just change by a tiny bit one of the variables that I have on the right-hand side? So you may see impulse response functions as a way to represent the same spirit of multivariate regressions. In a multivariate regression, each coefficient just captures the partial effect of one variable on the right-hand side on the dependent variable. And here you're trying to do the same in a system. So cutting through the complexity of the fact that in a VAR, everything determines everything else. So bottom line, you don't want to shock the U's, you want to shock the epsilon. But if you want to shock the epsilon, then there are some transformations which need to be applied, because you know that the epsilon, they are structural residuals. And so you know how you go from epsilon to U. So you just multiply the epsilon by the inverse of B. This implies that if instead of pre-multiplying the epsilon by the inverse of B, you pre-multiply the U by B, so the inverse of the inverse is the original matrix, you will have the epsilon themselves. This is basically what happens in these 2 points of the slides. The point is that since we want to give structural shocks, the representation, the world representation that we care for is not the one at the bottom of the previous slide, although that's a respectable one, so you can go for that, it's a choice. But normally people want to deal, normally people want to deal with this object here. So that's a world representation of your VAR, in which the representation is written not in terms of u t minus I, but in terms of epsilon t minus I. And you can do that, all right, but if you do so, then you have to apply transformations to the theta i's. The theta i's cannot be used as they are. They need to be transformed into appropriate coefficients, and these coefficients, they are called phi. So the matrix collecting the coefficients is called matrix phi. And the link between the theta I and the phi is given here, so it's visible. It's just applying the usual B-inverse transformation that we have encountered already. Now, the elements of these matrices phi, which are not the original A1 matrix to the power, and they're not the same as the theta I coefficients, they are transformations of the theta I, the elements are called impact multipliers. So what eViews or whatever software you're using is doing for you is to take the A1 matrices, to take powers. The powers of the A1 matrix, they are the theta i's. But then once you check, so once you give the input that you want to give structural shocks, the theta I are in their turn transformed into phi by essentially pre-multiplying them by the inverse of B, so by the usual triangularized matrix. And once you do that, then you have your impact multipliers. So the impulse response functions are, I can't understand, I just fixed this. The impulse response function, I will show you what I mean. The impulse response functions, they are sums of the phi coefficients inside the, so you need to erase these 2 here, and it's posted okay, and I have prepared slides which do not have it, but then when I come to class, I always find myself with the wrong set of slides, probably because I did not upload it again. So these 2 that you see should not be there. It's not already in the slides that you have posted, so maybe there is nothing that you have to do, so don't worry, but it should not be there. So essentially, if I take the coefficients from the matrix phi, and I just sum them over time between 0 and some point, like 52 in the plots I showed you before, that is the impulse response function that you have. Okay, now what's the problem of all this? Beautiful, fantastic. The problem is that there is not one single way you can go from the u's to the epsilon, or vice versa, for that matter. And the reason is that you know that if you want to estimate the reduced form representation of a structural VAR, you have to identify the structural VAR first. You have to impose restrictions which allow you to understand what is the precise connection between the U residuals and the epsilon residuals. So how the U residuals depend on the epsilon residual. So because impulse response functions depend on the phi, phi depends on theta I, and theta I depends on how you have identified your structural VAR. Unfortunately, impulse response functions, they will depend on the selections that you make when it comes to identification of your VAR. So this is to say that there is not just one set of impulse response function. There is a different set of pictures per every possible way in which you can identify your structural VAR. So if your structural VAR is born as a reduced form, it is already identified, and there is only one set of picture. But as you know, otherwise, there are infinite ways in which you can identify a structural VAR, and as such, there are infinite sets of pictures that you can offer to your boss if the boss is asking impulse response functions. And so what do you do? Well, the same things that we said yesterday apply here. Some people have very good ideas based on theory, experience with the data, models on how to identify their structural VAR. So they will apply that idea and produce one set of pictures. Fantastic. Some other people will not have good ideas. And so what they will do is to produce a few set of pictures and try to convince themselves or their boss that the pictures are not very different. So the impulse response functions you get are not very different from each other. So they're kind of consistent across. And so the exact scheme applied to identify your VAR is not important. And finally, there are ways, which I just mentioned, they're not in the slides, in which you can generalize the problem and basically impose all possible restrictions or possible schemes. There is an infinity of them, right? And then you kind of compute the weighted average of them, and you plot that. Okay, in eViews, you will see that it's just a click to do the last thing which I described. So in this slide, there is something which I explained already, paradoxically. That's why yesterday I was a bit lost. I couldn't find the slide because it is here. So some people, they see this business of identifying structural VAR by triangularization as a business of decomposing covariance matrices through Cholesky factorization. And the reason is here, because when it comes to trace out impulse response functions, you can see triangularizing as imposing a specific triangular nature on the covariance matrix, which basically takes you from the shocks epsilon to the shocks u. Okay, so they are equivalent. Again, same problems that we mentioned yesterday apply here. So every time you apply a Cholesky identification, a triangular identification, a Sims identification, call it as you want, they are all equivalent. You're imposing a strong asymmetry across variables because they are variables which are considered autonomous, I said yesterday, so very primitive, in the sense that the contemporaneous value of the variable just depends on its own shock. There are variables which are instead, to the contrary, very dependent on the others. So their contemporaneous value depends on the shocks of itself and all the other variables. And if you have more than two variables, there are intermediate cases. So there are variables which just depend on a few shocks, but not only on their own. And which variables end up of being of the first type, or the second type, or the third type is you choosing. It is a subjective choice. So by choosing the ordering of the variables through which you triangularize the matrix B, you're making this choice. And important, therefore, you are contributing sometimes in a heavy way to the shapes of the impulse response functions that you will report. So implication, so let me just show you the picture. Suppose you come in with this data and you show me these impulse response functions, just the picture, and you say nothing else. And my reaction should be of two types. First is ask you, so I mean, is this a reduced form VAR or a structural VAR? If you say, no, it's a structural VAR, you say, okay, how did you identify the shocks of the structural VAR? And then you will have to tell me things. So there are many ways to do that. You can show me a triangular covariance matrix, that's all right. You can show me a triangular B matrix, that's equivalent. Or you can show me something like you see here to the left of in the box of the slide, which is basically what kind of relationship do you have between the U's and the epsilon. Okay. The second reaction that I could have is, so what? Because clearly, if it's a structural VAR, you're showing one picture out of an infinity of pictures. And unless you show me a movie, so a sequence of them, I will never know whether the other pictures, they are similar to this one or they are very different. Also, when you triangularize, remember that you're setting the first variable on top of the ordering to be autonomous from the others in contemporaneous terms, meaning that that variable at time t just depends on its own shock and not on the shocks of the other variables. Here, this is visible in the first line in the box. So now I'm writing white. Okay, here it is visible in the first line of the box. So because U1 is the same as epsilon 1, it means that the first variable just depends on its own shocks and not contemporaneously on the shocks of the other variables. Fine. But the implication is that if I give a shock to any other variable, so to the second, say, to the third, to the fourth, the first variable, because the shock to the first variable follows the rule, which is in the red box, will not respond at time 0. So when you see something like this, see, this impulse response function is coming out of the origin, then if you just show me the picture, I will never know if either it's really coming out of the origin because the data want that, or it's you that by imposing some kind of triangularization made it in such a way that this comes out of the origin. And unless you add information about the triangularization that you have applied, this will not be understandable. So just recap. Impulse-response functions, they are nice ways to visualize the dynamic connections among variables. All right. Unfortunately, what we want to shock is not the user, because they are reduced form shocks and they are correlated with each other. If you want to give clean shocks, you want to shock the epsilon. Example, suppose you care for monetary policy and you ask, what if the ECB today states that they will do an extra 5 billion euros of quantitative easing? What happens to stock markets around the world? Fantastic, but you want to give a clean shock. So you want to simulate a situation in which only the ECB this afternoon is getting together and deciding this and making the statement that I just described. You want to block out all the other central banks from acting simultaneously, if this is realistic. If you give a shock to the epsilons, this is what you're doing. So it's a clean shock only to that variable and not to the others. But if you give a shock to the user, then you're simulating situations in which the ECB is doing something, but by correlation, also the other central banks contemporaneously, they are reacting to it. So it's like a collective multiple shock in which every central bank is doing something. Now, is that informative? It could be, because maybe reality is like that, but it's not a clean experiment. If you want to measure what is the impact of the ECB alone on stock markets, you have to shock epsilon and not you. Okay, so you want to shock epsilons. So the epsilon is the structural shocks, but the structural shocks, they are not estimable. They can be estimated, as we saw yesterday, only after you identify the structural VAR. And how do you do identification? There are infinite ways of doing that. You can identify VARs, remember from yesterday, by adding equations, so by pulling more theory into the framework. But what typically people do is to impose restrictions on the B matrix. They make it triangular, more or less. And this is equivalent to triangularizing the covariance matrix of the U shocks, as you can see here in the black box. These are equivalent things. But then you have to be careful, because the way you triangularize the B matrix is your choice. And if you make different choices, you can get different pictures. So impulse response functions are nice because you can look at them. They are useful because they draw lots of comments. But always remember that unless you're in some special situation, they are daughters of hypotheses that you have made. And so there is a bit of discussion to be had. Sorry. All right, so these are very simple impulse response functions. Is for the bivariate VAR, in which we have 1 month interest rates and 10-year interest rates for the US, 1990, 2016. And so the issue that I want to discuss in this slide is, why do we have 4 of them? Well, you have 2 series. You have the time series of short-term interest rates and the time series of long-term interest rates first. But then, because you have 2 series, there are 2 possible shocks you can give. You can give a shock to the 1 month yield, or you can give a clean shock to the 10-year yield. So as you can see, that's in the next slide. You can read this picture by column and by row. If you read them by column, then you are analyzing the reaction of both variables, short-term rates and long-term rates, to the same shock. And in this case, the shock is to the 1 month yield, the short-term yield. If you read them by row, that's the next slide, you're actually tracking all the possible reactions of the same variable, in this case the 1 month yield, to all possible shocks. So on the left, you have a shock here on the 1 month yield, and on the right, you have a shock to the 10-year yield. So it's always 4 of them. Sometimes in the past, I've asked in exams, how many impulse response function plots will you be able to compute and why? So be ready in case I do that again to explain where they come from. Now, suppose that always in the same situation, I ask you about how many pictures could you have? So panels is 4, and we saw why, right? There are 2 variables and 2 shocks. 2 times 2 is equal to 4. But how many pictures Well, the answer is in principle infinity, because if you're giving clean shocks to the structural residuals, then there are infinite ways through which restricting the model, the B matrix, the sigma matrix, the coefficients of the model by adding equations, whatever, there are infinite ways in which you can identify the structural VAR, and so there are infinite copies of this picture. And I repeat, the hope is that they all kind of look the same. But if they don't, some of them are different from the others, then you are in trouble because it's not obvious which one makes more sense, which one is closer to reality, and which one is not. Other comments. Now, even though those pictures were to be different across different identification schemes, they need to share something, which is better seen here. In the long run, so if you extend the horizontal axis towards infinity, they all have to go to the same place. So their long-run behavior, say here, 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 and so forth, should not much depend on the identification scheme. But that's interesting, okay, because it means that if you care for the long-run effects of a shock, the identification scheme is less important. But it's almost trivial. Why? Because if the VAR is a stationary one, you know that the shocks eventually must be forgotten. And so all these, say, schedule, all these curves, they must go back towards zero eventually. And in this case, one of them is doing that. But all the others, they seem to point, no, actually, two of them are doing that, kind of slowly. But two others are actually pointing in the opposite direction. Same comment as before, these are impulse response functions for interest rates. Interest rates are highly persistent, so they forget slowly past shocks, even though, trust me, they are stationary. In this case, they were stationary. Okay. Now, here you see a number, minus 0.0027. And if you want to see how you compute this number, maybe you are attracted by the fact that there is a specific number. If you go to this example, the explanation of this example in the book, there is a calculation of the number. Why? Okay. Now, can you tell in advance whether the impulse response function you are feeding to your boss will be influenced by the identification assumptions or not? Well, yes, you can. Generally speaking, after you estimate a VAR in reduced form, you will be offered the covariance matrix of the residuals, the reduced form residuals, right? And if the covariances, if the correlations of the use in this covariance matrix implied by this covariance matrix are generally small, say all of them, most of them are not statistically significant, then you have a situation in which it's unlikely that applying one identification scheme or another will make a major difference. If instead the correlations between pairs of use, they are high, they are statistically significant, then probably the identification scheme will matter a lot, and then you need to sit down and convince the others that what you did makes sense. Okay. Now, this is very important because for those of you who will do quantitative work, or those of you that in any case will care for interest rates and exchange rates, these methods are used even in common language. So people do things, bam, they show you an impulse response function. This is how the Swiss franc, euro exchange rate reacts to decision by the Swiss National Bank, something like that, right? And you're like, well, okay, nice. They're easy to read. So like in this case, you say, well, at the beginning, there is a positive reaction. It gets weaker and weaker. Then it crosses zero and it becomes a negative reaction. But it's never a strong negative reaction. And I know that if the VAR is stationary, we'll have to go back to zero. Fantastic. But if they do not tell you anything about the way in which they identified the model, the structural VAR, you know nothing. You're just looking at the picture. And they may be hiding a very different picture they do not want to see. So you're a portfolio manager, you take decisions on what to do, but you shouldn't because you do not have the full picture. Now, typically, impulse response functions, these ones are a bit more interesting because they are for a model with 4 variables, so more complication, but they behave in a more decent way, as you can see. they come with confidence bands. What is typical is to report 95% confidence bands. These are the dashed red lines. And the way you use them is very simple. If the 95% confidence band in correspondence to one horizon, say here 45, includes 0, then the response function in correspondence to 45 is not statistically significant. If it doesn't include 0, it is statistically significant, like in this case. It is a negative and precisely estimated reaction. So for instance, in this case, apart from the first two legs, there is no statistically significant reaction, so it's not accurately estimated. So it looks that the 5-year yield is actually dropping, at least after 5 weeks, more or less, in front of a shock to the 1-month yield. But you cannot really say that because there is so much uncertainty about the actual reaction that it is practically 0. And the number here is, in frankness, quite small. Same for the reaction of the 10-year yield. But the 1-year yield is actually reacting in a quite a precise way. Initially, it goes up just by a fraction of 1 basis point, maybe. It is statistically significant just for a couple of weeks. Then for a while, it goes back to 0, and it's not statistically significant. But starting about here, which is 8 weeks, roughly, it becomes again statistically significant, and it is a negative reaction. So if you increase short-term rates, you end up after a couple of months decreasing 1-year rates. That's what the data are saying. But again, remember that if I change the identification, which indeed is not reported, I can tell you what the identification is. I put on top the 1 month, then the 1 year, then the 5 year, then the 10 years, which is a debatable identification scheme. If you change the identification, you may find different pictures and different results. Okay. Right. Now, this type of experiments is typical. So you find a lot of them done in the literature, but not only the academic literature. You also find lots of stuff on Google if you look at the research of quant desks. Because it corresponds to operations of tightening or loosening of monetary policy by central banks. Now, the central bank is actually not controlling the 1-month treasury bill. It's controlling the federal funds rate in the US, the EONIA rate in the case of the ECB, so very short-term rates. But the empirical correlation between the policy intervention rates of central bank and the 1-month rates is so high that practically you are looking at the same thing. The correlations are in excess of 0.985 usually, so 0.99. But that's monetary policy, is not econometrics. All right. Now, some people, they want to ask a slightly different question, which is not how a variable reacts to a pure shock, but what is the percentage of the total variation of a variable which is explained by shocks to the same variable or to other variables? It's like a decomposition effort. So it's like, taking the R-square of the variable and decomposing it in the contributions to the R-square that the variables on the right-hand side of a regression are giving. These R-squares, maybe you have encountered them in econometrics 1, I don't know. They're called partial R-squares, and that's kind of a similar exercise. Now, it turns out that this exercise is equivalent to plotting impulse-response functions. It's kind of the integral of the impulse-response functions. And so it has the same strengths and the same weaknesses. The strength is that it's generally interesting to ask this question. The weakness is that as the impulse-response function depends on the identification that you have applied, the same happens here. If you change identification, you will change the result that you may get. So the idea is that if you take the forecast errors, the residuals, if you want, of your model, so these UTH equal to YT plus H minus the conditional expectation H periods forward, you can show, so you can do algebra that proves that such forecast errors, they can be decomposed in the way that you see in the slide here. They're just basically weighted sums where the weights are provided by matrices of structural shocks. There is algebra to do for that, but it's not scary. So what is the intuition? Well, the forecast error that you make between time t and time t plus h, variable by variable, is equal to the cumulant of the structural shocks that will happen between the next period and the final period of your forecast horizon, in which this cumulation is done with weights, and the weights are provided by these phi matrices, where the phi matrices are the ones that we encountered 10 minutes ago. They are the impact multiplier matrices. So what are they? They are complex combinations of the original matrices of the model, the A1 to the power, but they are combined with the inverse of B. So they are reflecting the identification assumptions that you have made. Now, what people do is normally to take the total variance of a variable at some horizon. So when you forecast at horizon H, so it is this guy, and use the decomposition. So use the sum that you see here on top to actually decompose such total variance in the portion coming from, say, the first variable, the portion coming from the second variable, the portion coming from the third variable, and so on. Now, in my example, I just got two variables, and so the decomposition goes like this. There is a portion coming from the first variable, the shocks to the first variable, and a portion coming from shocks to the second variable. And how big these two portions are depends on the impact multiplier coefficients. So the phi 11, phi 12, and so forth at different horizons, and square. Square because we are decomposing a variance. So the coefficients, once they enter the variance, they have to take a square to be able to work. I mean, that's what the algebra implies. And last thing, if you take each of the portions that you have here, so the portion which is attributable to the first variable, so let me highlight that, that's this one, and the portion attributable to the second variable, which is this one, and you divide by the total, which is the total value that you got on the left-hand side of this expression. So you take the red and the blue, and you divide by the left-hand side. The two numbers that you get out of it are the proportions of variance of the forecast horizon, which are explained by shocks to either the first or the second variable, and the resulting attribution, the resulting decomposition, is called the variance decomposition. To be precise, it should be called a forecast error variance decomposition, because we are not talking about residuals, we are talking about forecast errors. Okay? But so what happens in the background of your software? You choose your VAR, you choose P, you choose an identification scheme, you push the button, you do estimation, and automatically, for whatever forecast horizon you have in mind, these phi are computed. They are very simple transformations for a machine, and they're stored. Once you click over variance decomposition, they are retrieved, and they are placed into, say, ratios very similar to the ones that you see in this slide, and you will get numbers coming out. Now, remember, those numbers are a function of two, say, operations that you have done. First operation, you have identified the model. So because we are talking about epsilons, and the epsilons, they are a function of the use, you can go from the use to the epsilon only if you choose an identification scheme, because otherwise you don't know what the structural errors will be. Second, well, they depend on parameter estimates. So your sample enters the exercise through the A1 matrix. The A1 matrix is now known. It will have to be estimated on the data. And then the estimate of the A1 matrix will be plugged in, and these calculations will be performed, everything in the background. So you will not see anything, and this will take like a second or less than a second. That's the beauty of it. Now, the output that you get is kind of this one. So this one is the variance decomposition of the 10-year yield in the previous analysis. So the one in which you had 1 month interest rates, 1 year, 5 year, and 10 year. And the sample size is 1990, 2016. The data were weekly data, okay? And the ordering, Cholesky ordering, triangularization ordering, Sims ordering, which I am applying, is the one that you see here on the side. So I put on top the 1 month interest rate, meaning that's the most autonomous variable. So when something happens, when some shock happens in the 1 month treasury bill market, it impacts that market and all the others, But the shocks which happen in the other segments, in the other maturities, so 1 year, 5 year, 10 year, do not contemporaneously impact the 1 month maturity. So it's like the 1 month maturity is kind of isolated from the rest, contemporaneously speaking. So only the shocks to that maturity, they stay there, they propagate elsewhere, but the shocks from elsewhere do not contaminate the 1 month maturity. Now, in reality, that's a good assumption, because the 1 month T-bill market is very liquid. It's populated just by institutional investors, in the sense that I think the minimum cut to trade treasury bills is $5 million, right? And there is a heavy interventions by the central bank, not directly, but kind of almost directly. All right. Then I put the 1 year yield, then the 5 year, and then the 10 year. So basically, I go down in the ranking of the variables based on maturity. Some people will not be very happy with this ordering. Why? Because we know that the 10-year yield, because of benchmarking issues, is a very active and liquid market in the US and elsewhere. So even though it may be less active than the 1 month interest rate markets, it will be more active probably and more autonomous in that sense compared to the 1 year and the 5 year. Also, the 1 year treasury bill market, as far as I know, is not very active. Although, I mean, it's money market, but it's kind of a weird maturity to trade. And I think that there is much more trading and information diffusion in the 5 year maturity than in the 1 year maturity. But that's my impression. Okay, so I'm not a trader in the US Treasury market. All right. So how do you read the table? So you have different periods from 1 to 12, and these are weeks. Okay. Second, you have the total standard error that you want to decompose. So this number here, 0.101, 0.158, and so forth, is the equivalent to the number that we wanted to decompose. One sec. The number that we wanted to decompose here, that's this guy. And then you have the decomposition. So before it was just 2 blocks, red and blue, because we had 2 series in my example, but here we got 4 series, so we got like 4 blocks. And these have to be interpreted, one sec, these are percentages. So they should sum to 100, sorry. Let me see if that is the case. 62 plus 37, yes, they do sum to 100. I say this because there are some software which have kind of a residual, so I don't want to explain why, but generally they are close to 100. Check whether they sum to 100 or not. And so what are they telling us? That if you want to explain the variation of 10-year yields at very short horizons, 1 week, most of such variation comes from shocks to the 5-year maturity, so 52%. And next, there is shocks to the 1-year maturity, 37%. And finally, 11% from the 10-year, so they are like own shocks, and almost nothing from the 1 month yield. Now, somebody looking at this, if you haven't encountered this model, this theory in your studies, would quickly run to the conclusion that probably the expectation hypothesis is rejected. Because according to the expectation hypothesis, you should expect that the shorter is the rate, the biggest it is the role in determining long-term rates, which here doesn't really happen. Now, at longer horizons, let's go down here, the picture is kind of the same. We don't see big differences. Now, some people would consider these results a bit wacky. I mean, not really, a bit strange, okay? And why would that be so? Well, because the Cholesky ordering we are using is good in the first item. So the fact that we put on top of everything the 1 month yield is okay, probably. But the rest of the ordering, I would not approve it. I find it very strange. Now, indeed, if you change the ordering and you do all the calculations, here is what you get. Something totally different. Now I put the 10-year yield on top, which is also sensible. Some people would argue that most of the trading in financial markets, actually, central bank or not, happens in the 10-year maturity. Now, once upon a time, this would have been a reason to have a fight, okay, with somebody. Nowadays, with QE and central banks directly buying and selling long-term bonds, I don't think it's worth a fight. I think it's a sensible ordering. So 10-year on top, then 1 month, then 1 year, and then 5 years. There can be some fighting left on whether you should put on top the 1 year or the 5 years, but let's leave it there. Okay, the numbers are totally different. So the object that you are decomposing is the same. So these columns of number, if you go back to the previous slide, this one never works, never. Okay, this column of numbers is the same as before, but the percentage decompositions that you get out of the exercise is totally different. So at very short maturity of 1 week, 100% of what happens in the 10-year yield market is determined in the 10-year yield market. So it's like a closed market in which what happens outside doesn't seem to matter. Only for longer forecast horizon, kind of long forecast horizon, like a 3 months, 12 weeks, this number goes down from 100 to just 99.7%. And there is a bit of influence coming from the 1 month yield and the 5 year, never from the 1 year, which makes sense because the 1 year is a very strange maturity that people do not trade very much. Okay. Now you will see more examples in the labs. Some of them I will do it in front of your eyes, but especially the recording will have a full exercise on discussing these issues. Okay, last step, Granger causality. Now, if I show you this picture, I think that it would be in order to comment that the 10-year yield forecast itself, and it cannot be forecast by other variables. If it were forecastable using other variables, then it would show up somewhere here. It does not have to be forecastable using all the other variables, but at least some of them, but it doesn't look like. So based on this ordering, we are finding a situation in which we have some doubts on whether there is a causality link from shortened maturities to the 10-year maturity. And we could use similar variance decomposition to ask the opposite question, whether long maturities can cause the shortened maturity. So we will have to do more calculations. Okay. Now, this is one way to go. So variance decompositions and therefore impulse response functions, they provide the information, but is not the main way to go. The main way to go about it is to study systematically in a very simple way. You will see what I mean. Whether there are variables in a VAR that can forecast other variables, but these variables that can forecast cannot be predicted by other variables. And when this happens, we will say that VARs, they contain relations, situations of block exogeneity. So there are sets of variables which influence the others, but they cannot be influenced by the others. So they are said to be block exogenous. Now, I don't know if it was in this class as always, but some of you made a comment, I think yesterday, very much pertinent, because he was saying, well, but this business of killing things inside the B matrix, is that not to be related to whether the variables are exogenous, not exogenous, they are impacted, able to impact, and things like this? Totally right. And the way you test this is through running tests of Granger causality. So sometimes these tests, they are performed before imposing structural restrictions, because they help you in forging good structural restrictions as opposed to bad ones. What do you do? So there is a long definition, which I will not read, okay? But the point of the definition is that if you find a subset of YT, call it XT, which can forecast YT, so the remaining portions of YT, but it cannot be forecast by the other portions of YT, you said that XT is Granger causing such other portions, but is not Granger caused. And when this happens, XT is said to be block exogenous within the VAR model. Okay. So for instance, when XT is Granger causing, I'm reading here, YT, it means that XT can forecast YT, but YT cannot forecast XT. If you write that XT is not Granger causing YT, then it means that XT cannot forecast YT, and possibly YT cannot forecast XT, but this is not written explicitly in the formula. So let's see if I forgot anything, because I skipped the definition, but I want to provide the same intuition. All right. So technically, one needs to actually comment this. So what does it mean that a set of variables x can forecast y, but y cannot forecast x? So a set of variables x can forecast y when the mean square error, the mean square forecast error of a forecast of y that drops x is significantly lower than the mean square forecast error of a forecast which includes, besides the past of y, also the past of x. So that's the beginning. So essentially, the intuition is clear. If removing x, you get forecasts which are worse, then x needs to be included, and then you say that x is Granger causing y, and otherwise you don't say it. That's very simple. Okay. Now, unfortunately, VARs, they are not always so clean from this point of view. So there are VARs in which any subset of the variables forecasts any other subset, and vice versa. So any subset of the variables is predicted by the other variables. In this case, you say that the VAR is completely dominated by feedbacks, and you call the VAR a feedback system. So a feedback system is gotten when in the VAR it is really true that everything forecasts everything else. So everything depends on everything, which is the old motto of economics, of general equilibrium, usually, if you have studied that ever in your life. Now, let me show you how do you check whether there is causality using one example, as always, right? So the definition is the one I gave you, but what do you do in practice? So let's pick a case with two variables, y1 and y2. You can call them x and z, it doesn't matter. And let's pick a VAR2, okay? Just, you know, just not to always stick to a VAR1, but it's not a big deal. And as you can see, the VAR is written in reduced form. That's the beauty of it. To analyze Granger causality, because it is a forecasting problem, you do not need to go through the structural VAR, the structural form. If there is a structural form, fine, you get rid of it. So you turn it into a reduced form VAR, and you can use the reduced form VAR to perform the Granger causality analysis. So that's the sense in which a Granger causality analysis may be made prior to specifying the identification scheme that you want to adopt, which is the suggestion that some of you was giving yesterday when I was speaking. So what does it mean that, for instance, y1 Granger causes y2? That if you go in the equation for y2 and you compute forecast, including everything on the right-hand side that you see right now, you get a mean square forecast error. If you try to do the same forecasting exercise, dropping anywhere the legs of y1, so you drop these two guys here, and sorry, these three guys here. No, you drop y1. Oh, sorry, you have to drop these, and these. Okay, that's the right way to go about it. If you drop these three guys, you compute the mean square forecast error, and you see the mean square forecast error is dropping significantly compared to the original mean square forecast error. Then you say that y1 does not belong to the right-hand side, and y1 is Granger causing y2. Okay. So how do you test whether these three guys in blue, they belong to the right-hand side? So how do you know? Well, there is a way that you have learned in Econometrics 1 to do that. You deal with this as a regression. So you see this second equation as a separate regression. And what you want to test is whether B2, 1, gamma 2, 1, and delta 2, 1, they are all simultaneously equal to 0. And that's a null hypothesis which can be tested by applying, as you know, an F-test. So Granger causality test, or F-test, apply to the individual equations of the VAR seen as individual regressions. Okay. Now, there is another definition here, which is linear unrelation, which is weird, linear lack of relation, I would say, or linear independence, if you want. So you have linear independence when, if you test whether y1 can be dropped from the right-hand side of the equation for y2, you say, yes, it can be dropped. And, let me change color. If you test whether y2 can be dropped from the right-hand side of y1, so it means dropping this guy, and this guy, you will answer, yes, it can be dropped. So if all the variables, all the other variables on the right-hand side can be dropped without the forecasting power of the equations being affected, then you speak about linear lack of relation or linear independence. So linear lack of relation is the opposite of feedback system. In a feedback system, everything on the right-hand side matters and nothing can be dropped. In a linearly unrelated model, VAR, or in a model without any linear dependence, everything, all the other variables on the right-hand side can be dropped. And basically, the VAR simplifies to a bunch of autoregressive model, variable by variable, without any relations among the variables. Okay, now, careful. I know it's called causality, and if you speak to economists, statisticians, econometricians, and you say causality, will think about this, all right? So there is no much ambiguity. But if you go to the outside world and you speak about causality, they will think about more noble. So X causes Y when there is a mechanism such that when X occurs, Y also occurs, follows, say, occurs as well. But there must be a mechanism, an abstract or physical mechanism through which X is actually responsible for the event Y. In our case, we do not have this mechanism. We cannot know about this mechanism. All we are seeing, all we are testing is whether including some variables in the right-hand side of the regression can improve the forecast power for the left-hand side of the regression. And you can forecast because there is correlation. So you can forecast by chance. So notice, it's not just a contemporaneous relationship. So it's not just correlation. It's cross-seedal correlation, but it's a kind of correlation. So Granger causality, Granger-Simms causality, in fact, is much weaker than the causality philosophers are speaking about. Now, the issue with Granger causality tests is that if you have rich models with many variables, there are lots of combos that you can think about, right? So there are lots of subsets of variables you can shut down, measure the forecasting performance with and without them, compute an F-test, say, and see whether things work or not. And so one beauty that some softwares may have is that they do all these combos, all these combinations of tests for you, and they do that equation by equation. So for instance, that's the typical output of eViews. As you can see, there are 4 panels. So let me actually point them out. There is the 1-month yield panel, 1 year, 5 year, and 10-year. And inside each panel, let's use the 10-year panel, you try to exclude all the legs of each of the other variables. So 1 month yield year, 1 year, or 5 year. So these are the 3 sets of legs which you can exclude. And then you apply an F-test. Now here I'm invoking something that maybe you saw, maybe not. The F-test asymptotically is distributed according to chi-square, with the number of degrees of freedom equal to the number of restrictions that you are imposing. Now in this case, this table relates to the VR2 model that we have seen before in action. So anytime you shut down a variable, you are shutting down 2 legs. And that's why in each row, there are 2 degrees of freedom, because in each case, you're actually removing 2 legs on the right-hand side. And here you can read the p-values. So the p-values are large in this case. So the null hypothesis that the variables do not belong on the right-hand side cannot be rejected. So really, the 10-year yield is actually not depending in a linear sense, is not caused in a Granger sense by the other variables. Now at the bottom, then change color, otherwise it becomes messy. At the bottom, you can also test dropping all the variables together. So it's like a joint overall Granger causality test. So in which you're dropping on the right-hand side 1 month, 1 year, and 5 year. And you have your chi-square variable, 6 degrees of freedom. So 2 plus 2 plus 2 is equal to 6, and the p-value 0.6. So you can drop them all, and the 10-year rate is actually happy because the 10-year rate forecasts itself. Now, this is not a shock, because when we looked at the variance decomposition results for the VR2, so same data, same application, same model, that's what we saw before. So at short horizon, 100% of the shocks of the variance of the 10-year yield is caused by shocks to the 10-year yield. So that's completely consistent. Let me see. I mean, I think I'm done. Let me see if I forgot anything. Now, in red, in the slide, you have cases in which there is Granger causality. So it looks like the 1 month yield is Granger caused by the 1 year yield, here in red. And therefore, Also, in overall terms, all the other rates are actually Granger causing the 1 month yield. And it looks like the 1 year yield is Granger caused by the 1 month yield. So there is a block of variables, 1 month and 1 year, that's money market, in which they're Granger causing each other. So within that block, there is Granger causation, there is feedback, there is linear dependence. But outside that block, as you can see, there is not much going on. So it's like the treasury market in the US is separated into segments, the very short end and the long-term end, so the 5 year and the 10 year, which is quite plausible, right? It's a reflection of the so-called segmentation of bond markets, which is a common phenomenon that people have discussed and reported. But this is no longer econometrics, it's just comments about fixed income. All right, so done for the lecture and done for the day, and I will see you next week. So next week I will take about 50 minutes to start a new topic, which is unit roots, non-stationary processes, and next co-integration. But I will also play a little bit with EVs in front of you. I will play with VARs, and as always, I will optionally post a recorded lecture from last year in which there is a fully solved exercise about the VAR models, and how you use EVs to actually address those points. A small portion, like the last 20% of your homework, is about VARs, just the initial stuff, say, but so if you take a look at the lab, it will help you with the homework. All right. As always, guys, I will stick around for a couple of minutes in case you have questions or comments, and otherwise I will see you next week. Ciao. And I will stop the recording.